Warriors. What's up, Warriors? I'm going to go through the last 3 problems on the power drive so that you can see how to do these, how to set them up, and then you've got the complete power drive solution between the 2 days that we worked on this. So without further ado, we're going to go into this problem right here. John is in the bottom 10.2% of income for 22 through 25-year-old college graduates. If the average income for this age range is $30,000 with a standard deviation of 1,000, what is the most John could be making? Okay, so the first thing we need is to assume that this is a normal distribution, okay, which we can and always specify that in the problem. The second thing that might hang you up in framing the problem is, what is this? Is it a probability? Is it a proportion? And I think that's where a lot of folks get hung up. Well, income, number one, is a continuous numerical variable. Okay, so that kind of leads us that it is not a proportion, that it is a probability. All right. Another thing is we have a standard deviation with an average, okay, which is the same thing as a mean. Okay, so with a mean, this would be, if this was a proportion, then we'd have some kind of statement about the population proportion down here, but we don't. We have a statement about the population mean. So this is a probability, okay? And then the third thing is we think about, John is in the bottom 10.2% of income for all college graduates in this age range. So what that is saying is that when we draw the normal distribution and we say this is the mean here of 30,000, okay? Again, if it was a proportion problem, we'd have a P-pop, a proportion from the population to put here, but we don't. So what we're saying is that, why is it probability? Well, if we take all the 22 to 25-year-old graduates and we put their incomes here, we'll find a few way out here that are really making tons of money. We'll make a few down here. We'll find a lot here. And when I make these little hash marks, I'm stacking them because there's so many of them here. And there's the most really right about the mean. Okay, so if I took all those incomes and stacked them on each other, that's what this would be. So when I say the bottom 10.2%, we're talking about, if we drew a line about here, and this area right here is 10.2%. Okay, and then this area here for the rest of the curve is 1 minus 0.102. Okay, we convert that to a decimal. All right, so that's another way about thinking about the probability. It doesn't say the probability. The word probability is not up here. But you can't be thrown by that. Look for these other indicators and then think about it conceptually. And whatever way works for you, but this is a probability where this is a problem where we have a probability and we're trying to find out that single value x, which corresponds to that hash line right there. So this indeed is a single value x problem. Okay, so next thing we want to do is, well, we could do this a couple ways. You know, we want to find that value there that corresponds to that. So one thing that we could do is, let me just clean up a little area here. If you feel comfortable with it, is we could go and use the Excel inverse function. and we could find out, and we would just enter 0.102, and that should give us that single value x. So let's go ahead and do that. So okay, so that's going to give us a z-score. All right, negative 1.27. Okay, so I'm going to get rid of some things. Let me just wipe this down. Okay. So it's going to give me a z-score of negative 1.27, and I have some zeros down here. Or, remember, my probability was 0.102, okay, from this. All right, so I could, if I didn't feel comfortable with that inverse function, I could go to the z-table. And I'm looking for 0.102. So there it is right there. And just to be obvious, so remember, this is shrinking down like Mike TV, and I'm going to go in here and look for 0.102. And there it is. So from there, I'm going to go here first to find that negative 1.2, and then I need that hundredths place, so I'm going to go up, and that is 7. So I'm going to put that 7 there. So my z value is negative 1.27. Now, while I'm switching over, what I would like you to do is think about, okay, what do I do with that negative 1.27? You're at home watching this. And what would I do with that negative 1.27? Before I answer that question, well, let us remember where I am. Okay, what I'm trying to do is find out the x value that corresponds to that. And this says what is the most John could be making. So if he's in the bottom 10%, he's either making that amount or less. Okay, he's not making more than that, because that wouldn't put him in the bottom 10.2%. Okay, so back to this, what do I do with that value of negative 1.27? Well, I want to solve for x, single value, the most that John could be making. So I'm going to need a formula that solves for x. And that formula is going to be this formula. Z times the standard deviation, sigma, plus the mean. So let's see, do I have everything? Well, Z is that, negative 1.27. Sigma is 1,000. And then the mean is that 30,000. So x would be negative 1.27 times 1,000 plus 30,000. Okay, and that value is going to be less than 30,000, which makes sense because 30,000 is the mean, and this is 1.2 standard deviations left of the mean. Okay, so it's going to be less than 30,000. So that concludes that problem. So let's go on to the next problem. Okay, Warriors, we're going to do this other problem here on Christoph as a quality control expert in a box factory. Okay, so let me get my pen. All right, super. So the box production process is supposed to follow a normal distribution with an average of 3.5 inches thick with a standard deviation of 0.35 inches. Christoph measures the thickness of 20 boxes. If the sample mean falls in between 0.34 inches and 0.355 inches, Christoph will approve the shipment. What is the chance Christoph will fail the shipment? So, first thing that's probably helpful is to identify the type of problem. We see the words. What words cue us to that? Well, these words right here, sample, mean. Okay, so we have a sampling problem. And right off the bat, we're going to be working with X bar. Okay, we don't know what X bar is, but we have some potential values in the form of limits. So we could draw this problem like this. And we could put the mean here in the middle, 0.345. Okay, is the population mean? That's what this means, the production process. And the central limit theorem allows us to use that here for the sampling distribution. This red line is actually Christoph's sample with an n of equal to 20. So we can draw a line over here that says 0.34, and we can draw a line over here that says 0.355. And so if whatever X bar is, if X bar falls in between these two, he will approve. I'm just going to put approve. If it falls out here, he will not approve. I'm just going to call this NA2. And if it falls out here, he will not approve. What is the chance Christoph will fail the shipment? So with all that put together, we have a sampling problem. We're dealing with X bar, and our type of problem is where we have X bar, and we want to determine what is the probability. Okay? And in this problem, we want to see what we define that problem is probability in terms of NA1, whatever that value is that corresponds to this probability here, with this probability here, which is NA2. Okay, don't be confused by the fact that these are in decimals. Sometimes that is confusing, and you got to train your brain to discern from a value versus a probability. And then you have z-scores in there as well. So I understand that I can empathize. It gets confusing for me too. Slow is fast. You just got to know and do reps to keep good knowing what you're doing. Easier said than done. I understand. Okay, so first things first, we are going to, let's start. And you may say, well, I don't have a value for X bar. I mean, it says if it falls in between these two, but what is it? Well, you don't need one because you have these outer limit values, okay? So the way I like to do these problems, I just take one of these values at a time, okay? So we're going to work with this. And essentially, this line says, okay, and we want to find this blue area here, then we want to say, okay, if the sample mean is 0.34 or less, what is that probability? And that would give us NA1. So to determine that, we're going to use, I guess I'll pause for a minute and let you think about what formula we need to use to determine that. Well, to determine that, again, we need a z-score. The z-score is not the probability, but the z-score will help us find out the probability. So we're going to find out the z-score, and we're going to use 0.34 for that value of X bar minus 0.345. And we're going to take sigma, which is 0.35, and we're going to put it over the square root of 20. Okay, so we're going to figure out all that, and then we're going to go to our z-table. And what I'm going to do for this video is I'm just going to leave that up there, and then I'm going to go to my z-table here in a minute, so I'm not bouncing back and forth. Okay. And then what I want to do is find out this one. Now, here's something that is kind of tricky in this particular problem. So you might think, oh, well, this area here is equal to that. Well, it depends on how this interval is organized around the mean. And not all intervals are symmetrical around the mean. The distribution is symmetrical and always will be symmetrical. But these values, when we look at it, the dispersion is not symmetrical. 0.34 is 0.005 less than 0.345. But 0.355 is 0.010 more than 0.345. That means that this area here is a little bit larger than this area here. So what that means is that this area is a little bit larger than this area here. More importantly, that means that we can't just find this area and multiply by 2 on this particular problem. And we just got to be cautious so we know what we're doing. It's a little bit of an advanced problem, but that's okay. Let's talk about the setup here, okay? So the setup for this, we still need to find a z-score. On this one, we're going to find a probability, and then we're going to do a 1 minus, because essentially for this, if X bar was 0.355 or greater, we have to do a 1 minus. There's that Q. So let's do the setup. We have z. Again, we want to take that value for X bar, 0.355 minus 0.345, and everything else is the same, by the way. 0.35 and the square root of 20. Okay, so we're going to find a probability here and a probability here. So I'm going to go here to my z-table. And the first z-score that I'm looking for is negative 0.06. in terms of a z-score. So I'm going to go down here to the negative 0.0 column, and I'm going to go over 0, 1, 2, 3, 4, 5, 6 to that 0.06 column, which is 4761. See how that 0.06 column, 4761. And I'm just going to write that down before I go back into. All right, and then I'm going to look for 0.08. That was my right limit, 0.08. So I'm going to go to the other side of my z-table. 0.08, I'm going to start at that 0.0, and I'm going to move over to that 0.08 column. Okay, 0.5319. And remember, with that one, I'm going to do a 1 minus when I get over here. So I'm just going to go ahead and do that 1 minus right now. So that 1 minus is going to be 1 minus 0.5319. Okay, so that's 0.4681. And I'm going to add that to, well, I'm just going to write that down first, and while I'm still here, 0.761. .9442. So what is that 0.9442? Well, let's go back here. This is here. That's that 0.34. This is here, 0.355. We're trying to determine this and this. Okay, so we went to the table, we saw that this area here is 0.4761, and this area here is, to the left of it would be 0.5319, but we did a 1 minus, and so we got 0.4681. And we add this, so this number is Na2, and this number is Na1. And when we add those together, that equals 0.9442. So my drawing is probably a little deceiving. You may be thinking, well, that looks small and that looks small. But when you think about the distance from the mean, my drawing is probably not to scale. My drawing probably looks more like this. Okay? And another thing is that the standard deviation is 0.35. So if we just wanted to check ourselves, the first standard deviation occurs over here. Okay? We minus this, and so that's 0.310 out here, and then 0.37, actually 0.38 over here. So really, this makes sense. The probability, the chance that he will fail the shipment is here. High probability he'll fail it if it's out of specification. Okay, so just to beat the dead horse and draw everything over again and explain this in the real world. This is a very real world situation. I developed this box out of visiting York Container, and they actually have a quality control lab where they take samples of boxes and they do this sort of thing. And so when you think about it, it all makes sense. If we have a tight interval around the mean, and that means that, A, we want this standard. We ideally want every box to be this thickness right here. But if we can't achieve that, we don't want to be too far off. Okay, a box out here would probably be pretty thin, and a box out here would be way thick. And so we don't want to tolerate a lot of errors. So that means that we want our performance to be in this narrow zone right here. And we don't want to tolerate anything outside of that. So the fact that we have a high probability of failing the shipment if the sample average falls outside of that, that makes sense. The point is to get production to produce inside of that. Okay? So that's that problem. Okay, Warriors, last problem in this video. Peter wants to estimate how long the coronavirus remains on laminate surfaces. So we have some information about how long the virus stays on various types of surfaces, cardboard, paper, plastic, things like that. And we want to find out about laminate. All right, so he takes 20 measurements, gets a sample average of 72.5. So before we do anything, we could park that somewhere and say X bar equals 72.5 hours, and sigma, or excuse me, S, see what I did there? Almost made a mistake, happens. S is 4.6. So these two go hand in hand together. He wants an estimate that covers 99% of the possible values for the average of how long the coronavirus stays on laminate surfaces. So this tricky wording is always going to be there, so just take it one step at a time and frame the problem. So the first question is, what type of problem is this? Is this a single value X? Probably not, because we have a sample average. Is it a sampling problem? Well, he wants an estimate that covers 99% of the possible values for the average of how long the virus stays on laminate surfaces. So it's not necessarily that 99%, that alone tells us this is a confidence interval problem. But this word estimate is the same thing as a confidence interval. That's what a confidence interval is. We don't know the population mean, which is this, the average of how long the virus stays on laminate surfaces. We don't know what that is, and potentially we'll never know exactly what that is at this point. But we can develop an idea, a range of what that might be. So this is a confidence interval problem, and we are going to be working with a confidence interval for the population mean, mu. Okay? So right away, we want to work with this formula. So, which is the confidence interval for a mean, or mu, is we're going to use that centerpiece of X bar, because we have that. And now our $500,000 question, which is, do we know the standard deviation for this population? Well, that standard deviation is not that. That's the standard deviation of the sample. The question is, do we know the standard deviation for this population? And the answer is no. It's not provided, and Peter is essentially using a sample to kind of pave the way. So we've got to use t. And we've got to use the t value for alpha half. We'll come back to that. The rest of this formula is the sample standard deviation divided by the square root of n. So let's just go and see what we have. We have x bar. We have that. We have n, 20 measurements. So n is 20. The only thing we don't have right now is t for alpha half. So how do we find that out? We need two things to determine t. We need degrees of freedom, which is n minus 1, which is 19. And we need alpha half. Alpha half for 0.99, okay, so the first thing we do is we turn 99 into 0.99. Then we say 1 minus 0.99 equals 0.01. Well, that's alpha. To determine alpha half, we take half of that, which is 0.005. So alpha half is 0.005. Can't use anything Z here. We can't use a shortcut table, Mike TV table, or anything like that because we're going to the T table. All right. So I'm going to go to the T table and with 19 and 0.005 in mind. So first things first, I'm going to go down this left side, look for 19. There it is. And then I'm going to go to the right to 0.005, which would be right above where my cursor is. So 2.861. So I can go back here. Okay, so my t value .8. Now I forgot it. 861, I think. So I'm back, did some calculations, and so let's talk about where we were and how I got those numbers. So again, our confidence interval for a mu, our formula is going to be x bar plus or minus the t value for alpha half times sigma, or the standard deviation of the sample over the square root of n. And our values for that are x bar is 72.5. We have plus or minus. Our t value was 2.861. Remember how we got that. And then our S is 4.6. And our sample is 20. We'll put that to there. So once we do all that math, our confidence interval is going to look like this. We have that mu is going to be this, what I call the center of attention. It's going to be less than or equal to the upper value, which is this plus the product of these two. For that, I get it to work out to be 75.44. And then it's going to be greater than or equal to this minus the product of all this, which I get to be 69.55. So there we go. Our confidence interval, nice and pretty at the 99% of confidence. That means that this interval captures 99% of the values for how long the coronavirus stays on laminate surfaces based on this sample information. Okay? It's not right or wrong. We could take more samples, those kind of things, but based on the sample information, we think this interval does capture 99% of the possible values for the population mean of how long the coronavirus stays on a laminate surface once it gets put on that surface. And that's between 75.44 hours and 69.55 hours. So again, finally, the recap of this video, we did 3 problems from the power drive. If you have any questions, things that you didn't understand, please get hold of me. Otherwise, stay organized, focus on why we do these things, get your formula sheet set, and keep repping out with that formula sheet. This is built on repetition, and after a while, you will be able to do any problem that is thrown at you. Take care, and warrior on.